Momentum was great. Conservation of momentum is even better, much more practical, similar to conservation of energy, more practical and useful than just energy calculations. So I've mentioned this before. I said there's 3 conservation rules. I guess depending on if you classify linear momentum and angular momentum as different things, there's 4, right? And angular momentum we won't study in high school. But linear momentum is what we're doing today. Remember linear, grade 9 math, right? Linear is a straight line. So we're dealing with things, could be in 2 dimensions, but the idea is an angular momentum is the momentum of something spinning, and we just don't deal with that in high school. We deal with things traveling in straight lines. Okay, so COM is what I call conservation of momentum, specifically linear for this year. And the statement of conservation of momentum is just that given net force is 0, and what I mean by that is there's some sort of interaction, and usually it's a collision, right? And the only force involved is that sort of being part of a collision. It's not like 2 things colliding and something else happening at the same time. There's only one thing happening, and that's an interaction. Like I say, normally a collision. So the momentum of the system before the interaction or collision is equal to the momentum afterwards. So the equation, this is the equation. I mean, and really, we don't use the top one. We use this bottom one, okay? So the equation you want to, write down on your formula sheet that you'll use over and over is this right here that I just circled, and I'll make it a different color. But this is the one. This is the, this here is just saying I have 2 objects, A and B, and this is the sum of their momentums beforehand is equal to the sum of their momentums after. But we care about it in terms of masses because we don't measure momentums, we measure masses and velocities. So these are the same equation, this is just the one we use, okay? And the idea is I'm talking about 2 interacting objects. Theoretically, you could have 3 interacting objects or 4 or 5. It's just that you don't often, right? You don't often have 3 things running into each other at the same time. You can, and you'll see questions where there is, but sort of 90% of what we do is with 2 interacting objects. If it was 3, then all you do is you add MCVC1 on this side of the equation and MCVC2 over on this side of the equation. Okay, so I think I want to just try it, show you what I mean, okay? Sorry about this. Always this problem with my program that does this. So you can't see the whole example. Okay, so I'm trying not to do collision examples because that's a whole separate lesson. But in this case, we've got some kids standing on a raft. The student then starts to walk with a velocity relative to the water. So here's, the raft is, at the first, it's just not moving at all. Then it's free to move, and the person starts to move east compared to where the water is moving. What is the resulting velocity of the raft relative to the water? Neglecting any friction. That would be an example, by the way. If there's friction in the system, the net force wouldn't be 0, right? But we would never do that in this course, okay? So I'll just make east positive. G is the guy on the raft. R is the raft. So here's my formula then. Mass of the guy times, I'm not doing all the vector symbols, but initial velocity of the guy plus mass of the raft and initial velocity of the raft, before he starts to move, right? So 1 in this case refers to before motion and 2 refers to after he starts to move. And so the question is, where's the raft going to go? He starts moving east. What's the raft going to do? And you should figure that the raft will want to go west, right? Sort of to counteract his motion east. Oh, if you get thinking about this one too much, it'll drive you crazy, by the way. So just don't. Don't think, oh, what does that mean? It's going west compared to him or west compared to the water? Or just go through the math. Just do the math. That's what Niels Bohr said. Shut up and calculate. Okay? Don't think. Anyway, so isolating we're looking for the velocity of the raft afterwards. That's the whole thing you're looking for, right? So you isolate VR2. The initial velocity of the whole system, right? The raft is stationary. He's standing, so he's stationary. So everything at the beginning is actually 0. And then you just solve for VR2. Okay, so it's just rearranging that formula. And it's a reasonable number. It's going 2.6, right? The idea is this. there's no momentum to start. Well, if the student starts going with the bigger mass, by the way, 2 meters per second east, then the raft has got to go west to counteract that, and the raft is a little bit smaller, so to keep the momentums equal, right? So the sum is still 0. The speed of it has to be a bit bigger, and so that really does make sense. And I guess that's an important part of these questions, is to really reflect upon directions and speeds, and does the number make sense, thinking of whatever the interaction is. One more example, just on momentum. Oh, here's this problem again. So here we have what's going on is you've got some sort of, I call it an artillery shell, yeah, and it breaks into 2 fragments. And so they move in opposite directions of each other. And we know one fragment's 11 kilograms, and we know how fast it's going. Well, what's the speed of the second one? Okay, so they initially start at 0, they're just sitting here, then the thing explodes. So the smaller piece goes 95 meters per second. The bigger piece goes in the opposite direction, and we know it's 95. Oh, I drew the picture wrong. That was my bad. Oh, shoot. I screwed up the question. Will you forgive me? I don't want to redo it all. Just say the speed of the 24 kilogram fragment is 94. Just change that right there. Change that to 24 kilogram. So the bigger one's going 95. That's nice writing on my part. Okay, so this one's going 95 afterwards. So, I mean, before you can see the answer here, you pretend you can't see it. Pretend you can't see the answer. You should predict beforehand that the smaller piece has got to be going faster, because their momentum, they're going in opposite directions. The end momentum has to be the 0. The overall momentum has to be 0. So it starts at 0, right? So it's going to be 11 for the mass of the B times its new speed, or sorry, of A, times its new speed, plus the 24. So if we're calling this positive, so A2 is going to be negative, which makes sense because it's we know it's going to take off in that direction. It's going to be in the opposite direction, so it's going to have a negative velocity. And it's going to be a bigger number because sort of their momentums have to equal each other. They have to offset each other. Okay, so that number does make sense. I'm going to check mark it because it's a good answer. Okay, and that's it for the first day of conservation of momentum. The next set of videos will be on same idea, but specifically on collisions, when things collide with each other.